Hello and welcome to section 7.2 of our linear algebra notes. Today we are going to learn about quadratic forms. We'll do a little bit of sketching of them and some classification. So first of all, a quadratic form and this is a function on Rn. So the input is vectors in Rn and the output is given by transposing your input, multiplying by some square symmetric matrix, and then multiplying by your input vector again. One thing that's kind of interesting is that even though we're typically working with linear functions, this is going to give us things that are non-linear. And I'll show you what I mean by that in a moment. But in any case, the matrix A is called the matrix of the quadratic form. So first of all, if you use a certain special A, you get something nice out. So if we have, instead of A, we put the identity matrix in, well, multiplying by the identity gives back what we started with. And note that X transpose times X is the dot product of X with itself, which is the same thing as the length of X squared. So special values of A give special things when we do quadratic forms. And now let's take a look at what happens in general for a 2 by 2 matrix. So here let's let our X vector be x1, x2, and let's actually compute this. So first we write X transpose, which is, the X was a column and now it becomes a row. We have our matrix A, and then we multiply it by X back to being a column. So that's the same thing as going ahead and multiplying through by A first. So we have AX1 plus BX2, and then BX1 plus CX2. And then finally, we do our matrix multiplication, which remember we do our first entry in our first row times our first entry in our first column plus our second entry in our row times our second entry in our column. And so what we're left with, and since these variables commute, we have AX1 squared plus BX1 x2, and then plus another BX1 x2, and then CX2 squared. And so what you'll notice is that your diagonals are your coefficients of your squares, and then your off diagonals are showing up as your coefficients of what's called the cross term. Okay, so, and we could rewrite that as AX1 squared plus 2B x1 x2 plus CX2 squared. So that's how you go back and forth between the matrix and the actual equation, at least for a 2 by 2 matrix. And one thing you should notice, here's where I was talking about nonlinear. So notice that we now have an x squared. We have two variables multiplied by one by another. So we're getting something that's a little bit different. This is the only place this semester where we're going to do that. Okay, so now if we want to do this type, we kind of want to go backwards. And this time we're given a vector in R3. And so I'm going to write a little bit down here. So if we do x1, x2, x3 times a symmetric matrix, well, if it's symmetric, then we know that the first row has to equal the first column. And then we can write out the second row, but that means those e's have to reflect. And then finish off that last column. And so this is the equation that we're doing. And again, we are going to multiply our A times our vector. So we get AX1 plus BX2 plus CX3, and then bx1 plus dx2 plus ex3, and finally cx1 plus ex2 plus fx3. So first of all, our diagonal terms, well, they're only going to show up, I'm sorry, our coefficients of the squares are only going to show up once. We only have one spot where we're multiplying x1 by x1. Similarly, we only have one spot where we're multiplying x2 by x2 and x3 by x3. So what this means is that a equals the coefficient of x1 squared. D, I should have done that in pink. D equals the coefficient of x2 squared, and F equals the coefficient of x3 squared. So this tells us now, so we look for x1 and we see a 3. So that's our A, our coefficient of x1 squared. Our coefficient of x2 squared is D, and our coefficient of x3 squared is 5. So we our diagonal entries are the coefficients of the squares, and then the mixed terms show up in their own ways. Let's look at that. See if I can manage to erase without erasing everything. Okay, so our mixed terms, like for instance, for x1, x2, well, we're going to get an x1, x2 in our first row from the bx2 times the x1, and then also from our second row, oops, I want to still use pink there, when we multiply the x2 by bx1. And so that tells us that the coefficient of x1, x2 equals 2 times b. So that gives us, when we simplify that, that tells us that b equals 2. So that helps us fill in our next spot. And we also have an x1, x3, which has coefficient -6. And so if we look at x1, x3, we get it as a C from the first row of our AX matrix, and a C from our third row of our AX matrix. And so that tells us that 2C equals -6. So C equals -3. And then our final entry, by a similar process, is going to end up, I have run out of color, okay. So we have x1, x2, x1, x3, and what we're not seeing is an x2, x3, which we would get either by multiplying the x2 in the second column times the x3 in the second row, or in the x3 in the third column times the x2 in the third row. And notice that we have that term doesn't show up, so it's a 0. So that tells us that 0 equals 2 times E. So E equals 0. And now we have our matrix. Okay, so what we're going to do is to better understand these is we'd like to do what's called a change of variable. Basically, what we'll see in a moment is that we'd like our quadratic forms to be easy to draw a picture of what they look like. And so we're going to plug in a change of variable is either we replace x with some invertible matrix P times a new vector. And so if we think about what happens when we do this type of transformation, so first we start with x transpose AX, and we replace x by P times y. So everywhere we see an x, we replace it with a py. Well, using properties of the transpose, we get y transpose P transpose A P Y. And that's since Remember, whenever we do AB transpose, that's B transpose A transpose. Okay, but now this PA, I really should write that as our associativity. So that's, okay. I think that's the end of what I wanted to say about that. But excuse me. Theorem 2 in section 7.1 says that if A is symmetric, and A, it needs to be symmetric for these quadratic forms. Notice we are assuming A is symmetric. But theorem 2 says that if A is symmetric, then there exists some orthogonal matrix P, and remember that means it's a symmetric matrix whose columns are orthonormal, such that P transpose A P equals a diagonal matrix. And so if you actually take that, use that P as your change of variable, then you can plug that in and you get X transpose A X equals Y transpose D Y. And this actually eliminates the cross term. Or cross terms when you have more than a 2 by 2 matrix. And so to really see how we get at this, let's make the change of variable to transform the quadratic form given here into a quadratic form with no cross product term. So right now we have, here's the 6x1, x2 is our cross product term. Okay, so our first step is to write the matrix. I guess it's called the matrix of the quadratic form. And so remember that our diagonal entries are the coefficients of the squares. So we get -2 and -6. And then our off diagonals get split between, so we have a 6, which is split between the two spots there. Okay, because this is symmetric. Okay. And then the next step is to orthogonally diagonalize A. So you've been asking about why that's important, and so we're seeing it used here. I'm not going to go through that computation with you for today. So what I recommend you do is go back and make sure you feel comfortable doing this. So when we do this, we're going to get two orthogonal unit vectors. One is -1 over root 10, and I believe 3 over root 10. And then the other is 3 over root 10, 1 over root 10. And definitely go back and try to make sure you can get this. And if not, ask me about it, please. And then we need to make sure our eigenvalues match up with the eigenvectors we got. Okay, so this is our orthogonal diagonalization. And this says that A equals P transpose D P. So now we can write this 2x1 squared plus 6x1 x2 minus 6x2 squared as Y transpose times our diagonal matrix times Y. And if we let Y equal y1, y2, then this whole thing ends up being -7 times y1 squared plus 3 times y2 squared. And so this is what I mean by eliminating that middle term. We no longer have, or that cross product term, we no longer have that x1, x2. And this is a lot cleaner. We'll see why when we try to graph it in a moment. And so we have a theorem that says if you have a square symmetric matrix, then there's an orthogonal change of variable, and that we call it an orthogonal change of variable if that P is an orthogonal matrix. that actually, and this should be x to the capital T, x transpose, that actually transforms this quadratic form into a quadratic form with the different variable with no cross product term. And so this theorem, what it really says is that you can always do this. Since every quadratic form is given by a symmetric matrix, there's always a way to change your variables so you don't have that kind of pesky form and cross term. And really the reason why it's so nice to do this is because when you, it's partly because of this drawing, the geometric interpretation. So let's fixate on the 2 by 2 case, but this works in higher dimensions in sort of a generalized way. So let's say you take your quadratic form and you set it equal to a certain value. So if you think about what's happening, we have Q takes on, in this case, since A is a 2 by 2 matrix, where our input is two entries, and our output is going to be a real number. And so if we look at, if we pick a specific one, like C, then what we're doing is we're looking at all the possible pairs, and you can start to think of this as X and Y that equal that constant. And so if you think of graphing it in 3D, you're looking at XY coordinates with output C, and you can think of that C as being kind of the Z coordinate. So in other words, you're typically used to having a function f of x equals y, and you draw it, you draw some function on the 2D plane where you draw your inputs and your outputs. Well, now what we're doing is we're doing q of xy equals z. And so we have our xy coordinates, and I think typically we draw it like that. And then we also have our z coordinates. And fixing a given z value is kind of the same as fixing a given y value. If I told you to pay attention to all the input values that give you a certain y output, that's kind of the same thing as saying, so if we have, and this is now going to be like some sort of surface type of thing, and we're kind of cutting it off at a certain z value. This is a little hard for me to draw, but there's some great pictures in your textbook. Okay, but so anyway, the point is that if you do this cross section, what you're going to get is either an ellipse or a circle. So you're either going to, and let me try to draw this carefully. So remember, this is a cutoff in the middle of your like cross-sectioning out your picture. So if you have an ellipse or a circle, then that's going to look kind of like this. So this is like a cross section at a certain height. And what we'll see is that that's going to correspond in the 3 dimensions to something that maybe looks like either like sort of a cup, like a bowl kind of thing, facing up, or it might be a bowl sort of thing facing down. And we've decided to chop it at one height, and that's what gives us this picture. It could just be 2 intersecting lines, and that's a situation in our, let me draw the 3-dimensional situation first. This is also really hard for me to draw, but this is on page 407 of your book. So you might have a situation where your curve kind of looks like a trough. And when you draw a cross section, you just end up getting lines. So you get like something that looks like that. Or you might get something. Wait, I think I left out, because you can also get a hyperbola. I did. I apologize. I left out hyperbola. Goes in there. And so this is the situation where you get something that looks like this. And this comes from a saddle in 3D, which is like next to impossible for me to draw. I'm going to kind of try, but you've probably seen these in calculus because you talk about those like saddle points. But yeah, this is coming from, I apologize for my drawings. This is still coming from a point, I guess. Let me kind of, if you think about it up there, if you look at your book, you'll understand better why this is actually going to give you these little curves. This is like, in fact, if you're like sitting on the saddle, you can kind of see that you've got like curves going through. Okay, so now we're going to attempt to sketch the graph of, and I apologize, this is going to be one of our longer videos, but I'm only going to give you one quiz question to kind of make up for that, of our problem from number 5 that we just diagonalized. So if we already had a diagonal matrix, so if we had no cross term, then the graph would be considered in standard position. But otherwise, we need eigenvectors, which are going to be our principal axis. So basically what we're going to do is we're going to take a new basis. And so if we go back to our example, we had an orthonormal, vectors, this negative 1 root 10 and 3 root 10, and then 3 over root 10 and 1 over root 10. And that's u and v, and let's see, u goes in the negative direction. Okay, so these kind of look, I'm not going to draw this really precisely because I can't do it very precisely anyway, but the idea is that they're pointing at a 90-degree angle from each other. And so now we have new axes, which are really nice because what happens is when we try to graph this, and don't worry about replicating this, okay? At this point, I'm just kind of showing you how this stuff works. To give you an intuition for this geometry, I would not hold you responsible for it. Because there's kind of a lot here, at least for this section 4 of this 7.2. So the rest of 7.2 is fair game. But this is our hyperbola. So this is a hyperbola. And so the main thing that I want you to get out of this is this idea that we used our orthonormal basis to give us an easy way to graph this quadratic form. So this quadratic form kind of naturally fits along that, this new set of axes rather than our original one. Whereas over in our very first example that we did here with our typical standard basis, this is in standard position because it's not shifted, whereas our example was shifted. Okay, so I think that, I have one other thing. Now this, I will hold you responsible for this last little bit. We have the notion of positive definite, which says that every single value, and I can keep my picture here, every single value of q of x is positive. We have negative definite, and that means that every single value is negative. There's also semi-definite, which means it's great, everything is greater than or equal to 0. And we don't care about the origin. So everything's positive except for the value at 0, 0. And then indefinite if you get both. And we have a really nice theorem that we're not going to go through the proof of, but that basically says you can figure out whether a matrix is, or its corresponding form, we kind of use those interchangeably, is positive definite or negative definite based on its eigenvalues. And so, positive definite is when your eigenvalues are all positive. Negative definite is when your eigenvalues are all negative. And then indefinite means you have some of each. And so finally, the quiz question for today is to go back up to this quadratic form, take a look at its eigenvalues. If they're all positive, then it's positive definite. If they're all negative, then it's negative definite. And if not, then they are indefinite. And we will stop there.